never see me because I would always be on the computer. She didn't quite like the closing statement, but I think the principle was there. So ever since 1982, I've been this has been the dream, and I've been working towards it, and doing various things to build up the technology base for this project. However, the real issue is that when I left when I left Google and retired, I really was ready to go on this, and I was 58 at the time, so I wasn't exactly, 1 foot in the grave. I had plenty of energy and time and the resources to make this happen. And what I decided to do was to try to do in the science domain the same thing I had just done prior to that at Google, which is, how do you create a culture and an environment of getting hyper creativity and sort of break free from sort of the traditional way of doing things? Mm-hmm. And so there was sort of, in building this organization, there was an idea that, well, something worked at Google, but it might not work somewhere else. So, if you try something twice and it works, it might even be durable.
A new model, right?
It's not really a new model. It's
not a new one. But
I'll tell you about where I learned the model from in a minute.
A question, yes?
Yeah, I have a question. All right, so right now your telescopes are focused on the visible spectrum, and I was wondering if at some point your company might include telescopes that are looking into other parts of the electromagnetic spectrum.
Right. I guess everyone heard the question, so I won't have to repeat it. Right. So, but the context for that question is visible as sort of light as we see it, and then there's a thing called very near infrared, which is out to 1 micron. The light we see, green apple, is around. Green is like 0.55. Blue is like 0.4. Red is 0.6. We can go out to about 0.1 with silicon, and that's sort of called the near infrared. And the redder you go with the light, the more you can see through dust. And so if you're looking at anything having dust, like planetary formation, being able to see through dust is really important. So that's why telescopes are infrared. We plan to add a second round of instruments where we will do an infrared capability that will go out to what's essentially called 2 microns. If you know the astronomy thing, there's HJK, there's 3 bands of color out there. So we can go out to 2 microns fairly easily. If you go out beyond 2 microns into this serious infrared, you need helium cooling, and the detectors cost more than one. The detector chip costs more than one of these observatories. So it becomes prohibitive for us. Also, infrared photons don't have much energy, so you need a big telescope to get enough energy to sort of get over the environment, the ambient environment. So it's practical for us to do some infrared, but not a lot. We don't plan to do radio astronomy or anything like that. It's too expensive. It's a big scale stuff. And I haven't been able to figure out anything that we could do that actually would contribute. And then ultraviolet astronomy, the short stuff, it's called the air stops it. So you basically have to be in space. And any kind of space program, even if you're camping on another project, is a $50 million project. And that's more than all of our stuff would cost. Did I answer your question?
Yeah, that was the question.
Right. It's really very, very expensive. And one of our scientific director was one of the major contributors to Kepler, which is a telescope that was launched this summer, which is basically doing extrasolar planet detections by staring at an area of the sky just from the outside, from outside the Earth, nothing in the way but nothing. And that program's coming along very nicely now.
Excuse me.
Just to take that another step further, I had read somewhere on the internet, of course, and it has to be true. You said that whenever you were at Google, you said that your engineers really didn't need managed, that they had what they needed was a very clear set of goals. And do you work that same sort of philosophy with your company now? There's a goal, and you allow them to
That's
do it.
That's exactly how we do it. There's let's see, 58 people right now worldwide.
Mm-hmm.
There are one or kind of two people that have managers, and that's it.
Right.
It's just a free-for-all.
Okay. With
But-
very clear goals, I'm sure.
We have a goal, groups have goals like engineering, mechanical engineering, people have goals. The goals are published, they're debated, they are not micromanaged, people are accountable in the sense that their simple professional pride says, I'm going to do it. And when I think they're sandbagging and they're setting too low a goal, I kind of beat them up and say, well, gee, I could do better than that.
Good.
Do whatever you need to do. So that the art is getting goals that are a stretch, but not impossible. Because there's no, a negative result in science is a good result, potentially. But failing in what you're trying to do is no fun. So the art is always to just have enough challenge that the person involved really can grow and be proud of what they do, but never let them get too deep.
My question is, with this global telescope system, there are some capabilities that are really unique. And you mentioned, for example, watching supernovas, having all the scopes worldwide, monitoring it. They're all calibrated. As the Earth turns, you'd have different observatories keeping a watch on it, 24 hours a day. What are some other unique situations that you think this telescope network would lend itself to that would be really, contributory to science? Something that you're offering by building the system that just can't really be done today.
Well, okay, good. One, probably the most important one, is the one you just described, actually. When we think of supernovas blowing up, as I said before, they're a standard candle. You can use them to calibrate distance. But I said you had to classify them to figure out which type they are. Well, there's a bunch of theoretical types, including some that were developed at KITP, the Kavli Institute for Theoretical Physics here in Goleta, associated with UCSB, that have not yet been seen. And there were some other theoretical types that had not been seen, but one of our people, working with some other grad students at Caltech, figured them out and said, aha, unexplained one. It fits this model. It's the biggest supernova ever with the biggest star with a whole new set of physics. So what I think we're after more than anything in the world is to be able to find new phenomena where there's a lot of energy doing something in very short periods of time. So it's be there or be square, because it's gone by the time so you got to get there fast and then really get good at analyzing that kind of science. I mean, the observation is only hard. Drawing the proper scientific conclusion from that stuff is extraordinarily difficult, and that's something we really want to focus on.
The other thing I was wondering, with your background in computers, with the internet, in astronomy, and with engineering, you're in a unique position to really look forward to, basically think of the future of telescopes. What do you think are going to be some of the major advances in telescopes? I mean, when I was younger, autonomous telescopes didn't exist, so that's a big step, having them be able to track and find objects. I wouldn't have even thought of that. So, and with the understanding of